worked as an intern for Succinct this summer, doing formal verification of their RISC-V instructions with another intern, Gavin, and then Nethermind helped out a lot with this work as well. And then there's been sort of some ongoing things throughout the fall as well. But I'm going to mostly just talk about, I guess, what we accomplished over the summer and the state of things right now. Okay, so the overview, I guess, of what we're trying to do, we want to show that SP1's constraints enforce alignment with the RISC-V. RV64IM is the instruction set we use. So this is sort of a broad task, but it's sort of essential to have this in order to make the ZKVM verification work, but it's also sort of a self-contained piece. We want to show these mathematical facts align with the spec, and that's sort of independent of anything about the prover system or I mean, in theory, a lot of the implementation in general, it's a much more general thing. So I'll just say the high-level approach we have is to extract the constraints from each circuit into lean. We chose to use lean as the DSL for this because a lot of the other verification work has been in lean, and there's a lot of good tools that we have access to there. We map this representation to some sort of proposition about how the inputs are actually constrained. We model these in the sale monad. So the RISC-V backend that we use is this. The RISC-V spec we use is the one that comes from this lean backend for sale that was recently developed. And so we embed our computations in this monad, and then we show that it behaves identically to the sales spec. And I'm going to go into a lot more detail on all of these parts, but this is sort of in general what we're trying to do. And then at the end, we want to be able to say, okay, now we know that the constraints have ensured that we are actually behaving the same way that RISC-V would. So maybe more explicitly, the sort of trust and assumptions we're making with these tools is that we're using the lean kernel and this model of sale in RISC-V. So obviously we're trusting and proving things correct relative to both of those, but these are both like very sound things to sort of ground our proofs in. We have a custom extraction tool that we built for this to extract the constraints from Rust to lean. This is just an SP1 tool for symbolic execution. So, you know, there is maybe some more risk there. And then we also have some assumptions we make eventually in lean that I'll talk about more later. But then at the end, we want to be able to say that given that all of these things are correct, SP1 and RISC-V are behaving the same on sort of valid inputs or valid initial states of registers in memory. And we're not going to at all, and we haven't at all, done work on, you know, inductively saying that many operations in sequence, how those might behave. But for each individual instruction, if the inputs are in a valid state, we verified that they remain in a valid state and comply with RISC-V. So I'm guessing probably most people in the call know some lean already, but I'll have a slide on just some formal verification stuff in lean. So at the core language of lean is just this functional programming, just like OCaml or Haskell. Basically every proof assistant has this. You can define functions and do regular computational things, but you also have this definition of being able to write proofs and mathematical propositions. So here, this is a proof that 2 times 5 plus x is 10 plus x, and this is just true by definition. It's just reflexively true. And as we write more complicated proofs in lean, we use these tactic proofs usually, which say that we have a couple steps in the proof, and by the end it should enforce you should have proved the statement by the end of the sequence of tactics. say usually the things get much more complicated than this, but you don't really need to understand lean hopefully too much for the rest of this. But in general, we did pretty opinionatedly choose to write things in lean for this. Uh, so some context on what we're actually verifying before I describe sort of how we extract these constraints out. Uh, for each of the chips, so I'm going to be using JLR instruction as sort of the running example throughout this. Uh, your chip has a bunch of fields, and each of those is some field element, and our constraints are eventually going to constrain uh, certain things about each of these values, like that a value 0 or whatever it might be. And each of these values is really just a column index in a table. And when we do the extraction, we just extract things by these indices. So it maybe looks more clear in practice. So on the left is the Rust code for the JLR chip in SP1, and on the right is the lean code that gets produced by the extractor we have. So for example, on the left, there's this local.isReal variable, which corresponds to column 29. And the builder in Rust is asserting it's a Boolean, and when that gets extracted to lean via this symbolic execution of the code in Rust, you end up with saying, okay, the 29th column, which is this main of 29, either that value or that value minus 1 must be 0. So if you multiply them, we're asserting that that must be 0. And for each of the chips, it kind of just goes through like this. There's, for example, this subcall to an add operation as part of JLR, and this gets extracted to lean as a subcall to the extracted code for add operation. I think having that level of reusability is sort of the minimal necessary thing you need in order for this to be really feasible to verify things. And then, yeah, at the end, we're just returning a big list of all the constraints. So the central thing that's being extracted from every chip in Rust will be just a big list of constraints and interactions, which I'll talk about a little bit here. So I guess before that, there's, I mean, again, if you have some expression being built up, the symbolic execution will just build that up piece by piece. And then eventually, when you assert that some value is 0, it's smart enough to call back into that. And for maybe the more interesting thing is we don't just assert things are 0 as our constraints. We also have these table interactions. Because we're not doing full inductive arguments, we don't really need a perfect model of these interactions and lookups. For the purposes of verifying individual chips, what we're essentially going to do is say that in the DSL on the right, we just track that a bunch of things got sent, and we're going to later on just associate to each of those like some set of assumptions that we expect to hold. But to actually prove they hold, you would need a more global argument. But for now, we're saying, okay, we have this slice range check, which does four interactions with this byte table. And so we just directly extract these 4 interactions. And this is done completely by some scripts. You can run them regularly and see if things break or not. It's a pretty slow thing to build, not the extraction itself, but all the actual proofs. So it's not like you can run this like constantly, and it's also a lot less stable than something like Picus, which this backend that was developed for this work to do the translation I just showed has another backend also was developed for purposes of using Picus Paradise. So there is some flexibility in the extraction, but yeah, the actual lean code proofs we end up with are much more brittle than something you get there. Okay. So that sort of covers how we actually get the code into Lean. But the thing that we're getting out now are these just sort of meaningless uh, just entries or constraints. It's just an enum. So we need to actually associate some kind of semantics to it. Um, the most obvious one is if we have a constraint that asserts that something is zero, that just maps to the proposition that that thing should certainly be zero. And then we have a few other slightly more interesting ones. SP1 has some byte tables that it uses for a number of operations. So uh, the constraints for those need to come from lookups. And so uh, when these byte interactions happen, we just assume that those are associated with these values being enforced. And in future, we'd like to show that some actual lookup argument implies that those things are actually holding. But for this point, it's sufficient to just assume it and talk about each chip. So we have something similar with memory saying that the limbs of something that's being read from memory are all U16 values, so it forms a word. And there's this kind of mess of a one that's uh, I maybe don't want to go too into detail on it, but there's also this assumption about the program counter and some initial setup stuff. Uh, and then anything else, I guess, just maps to true. So there's many other interactions that happen, and most of them just get thrown out. We could perhaps be filtering out what we actually export to Lean, but we can also just filter them out here essentially. And just as an example, if I just sliced up a part of the JLR constraints that you get from the extraction, and it looks like this after you apply that state prop transformation. So it is really just a big statement, mostly about either columns being zero or bounded by powers of two for the most part. One thing that does come up is we end up then with these like quite long strings of just like many propositions, which at first many of our proofs were breaking these up constantly and inspecting for particular elements of this, and this was actually really quite brittle. So as I've been trying to work on maintenance and improve maintainability along the way, trying to do as little of that as possible is actually quite useful for making these more maintainable. And in particular, just like keeping all these facts in the context, applying stat solvers or these tools like this, rather than inspecting too close, tends to give you things that are a lot easier to work with long term, I would say. So we've now associated this proposition to our statements, and we can represent what the constraints are actually implying, but we need to actually say something now about the specific behavior of the program, because we haven't really talked about the inputs or the outputs, if you want to call them inputs and outputs. It's maybe a little misleading, but the main statement for each of our uh, operations will say something like we have this state, this sales state, which is an abbreviation for pre-sale sequential state. This is sort of the standard sale monad state, which is sort of not very clear here, but it's essentially just a map from registers to values and memory addresses to values. And we need to assume for SP1 a few random things globally, like there's a register that tells you what your privilege is, and that should be set to the machine. RAM in SP1 is indexed from 2 to the 16 to 2 to the 48, for example. There's also this sealant-based thing. There's a few I omitted, also just random register things which come up with sale, but we basically are assuming just that we have some map from registers to memory, registers to values and memory to values. And for each thing, for each possible register, it has some value. this is just saying that it's not a padding row, which is not especially important. And then that the constraints all hold according to the mapping I talked about before. And if that's true, then these op-A, op-B, and op-C, which in theory our extractor could just tell us what these op-A, op-B, op-C values are, but right now they're just manually specified. But the spec of how JLR behaves in the sale extracted the sale extracted spec should align with the one in SP1, where we're defining those as the spec one is this actual lean RV64D function plus a program counter incrementing, whereas the one in SP1 is manually writing specifically these two values. You can see in the Rust code that these are the two values being written. Again, there's sort of some trust here in that, okay, these are actually what is being meant to be the written values, but it's sort of low risk, and it is also something that can be improved later. But if we do have all the constraints holding and we're in a valid initial state, then when you run both of these computations, you should get the same thing on that initial state. And running here is just some, if you actually want to know what it is, it's the error state monad run, because SailM is really just a wrapper around an error state monad. But really you can think of it as just updating the registers and memory values as you run the computation. So all of our proofs essentially are saying, if the constraints hold, then we have some statements analogous to this. This isn't quite enough, though. There's actually one thing missing, which is that we're not talking about the memory arguments or what values are preloaded into memory, which is also important and something we can't prove from scratch operation by operation. So again, we need some sort of assumptions about this. The first of which, there's always this interaction with this state table, and we need that the thing that was written to the program counter is the thing that's actually in the sale state program counter. So that's, I guess, sort of always true. There's always exactly one of these interactions in everything. So maybe it's, you know, a bit redundant to put it here, but this is an assumption we need. And then we need similar assumptions about if you have something written to memory. In this case, if the address is low, so the address is less than 32, then we're saying the thing is a register, and the thing that's in that register should be the limbs. You have a sort of mirrored statement for memory, which the memory map in Sales model is in length 8 chunks instead of 16 chunks, so it actually has to get broken up quite a lot, but it's still just the same idea that we need this basic assumption. And again, in every other case, there's really nothing here. So, okay, what does an actual full proof look like? This is now div instead of JLR, but it's very, very similar. And I guess the thing I want to point out is the actual proof here, the goal is usually we try to isolate this to just talk about sort of this monad manipulation stuff, sale stuff, things like that. And then there's just this single line, this spec.div, that's actually calling into what I would consider the sort of the bulk of the proof or the meat of the proof. And by isolating like that, it can actually be really helpful in making it easier to sort of change the modeling and change things about sort of not the core mathematics. And then that's sort of isolated to fixing things in this sort of smaller proof here, and then the actual like bulk of the proof is sort of isolated on its own. And I will say also, this spec.div is not simple. I don't have the code in the slide, but I think it's, you know, it's a couple hundred lines. And
Is spec.div
oh, go ahead.
sorry, is spec.div it's like it's kind of a more of the proof is written there?
Yeah, I mean, I can actually show it, I guess. Spec.div is the one saying actually that like all of these mathematical facts imply the main reduction.
I see.
I don't know if stop sharing will rip the recording off, but
No, I was just curious.
I'll maybe come back to it later, but yeah, it is essentially.
Yeah, we can show it at the end, but it won't stop the recording if you switch what you're sharing.
Yeah, the problem now is I can't actually get back to what I was sharing.
Yeah, we can go back to the spec.div thing at the end this time.
Yeah, I'm just trying to find where the presentation was. Okay. Yeah. So yeah, spec.div just contains most of the mathematical reasoning, and then everything out here is mostly stuff that we're stuck with because of the sail modeling and things like that. And then some ongoing and future work. I think the main things have been focusing on making it more maintainable and being able to cover and reason about a broader range of things. So the first thing is we don't show ever that all of these assumptions that we make are preserved by all of the operations. So for example, if I go to here, there's this assumption that the program counter is a multiple of 4, which is just something that Sail RISC-V, I suppose, enforces on its own. And so in order for our things to make sense, we need it to be true at the start. And we also know that it's going to be true at the end because the value we write is exactly just the program counter plus 4. But we don't prove that those properties actually get preserved, which is something that we do actually want to show and know is true. And if we want to make inductive arguments or talk about memory arguments, that's also important there. So the DSL for the circuits in Lean, this model just using a list of constraints is essentially just, I guess list is maybe a monad in the simplest way, but there's definitely better DSLs. There's the C-Lean DSL is the plan, but I guess Alex would know who has been mostly developing it. Open.
There's a list of like 15 people, so maybe it's a bit long to read them out. But the main repository on the open compiler repo has all the names. I can list them out in the chat.
Yeah. So there's a couple reasons to want that. One is just that we can't really reason very well about interactions and lookups. We have this sort of axiomatic way to associate, say, okay, there's this memory thing, and we can talk about what goes into each value, but we can't actually really make the full argument that you'd want to make. And so having a DSL that supports that better is very good for that, and also being able to reuse components more and show equivalence between different components, which again, there's not really a good way to reason about that in this like list of constraints representation. And then the automation in the main correctness proofs can be hit or miss. I'd say when I changed, for example, well, I didn't change. When Succinct changed the prime field they were using, for example, then I was going to do the corresponding changes to the Lean proof, and you can see that some proofs, some ways of writing the proofs were somewhat sort of instant. Like I didn't really need to fix anything, and and in others, there's like quite a lot of work to fix. So trying to get that more uniformly maintainable, and I think a big part of that is using a lot of these tools, these sat solvers, things like that, to better automate and make the proofs more maintainable. Oh yeah, and I didn't leave the last one. But yeah, that's the major overview, I guess, of the work, the assumptions, what we have and don't have yet. Happy to answer any questions. Might have.
Yeah, go ahead, Shankara.
Oh, hey, for the first point about the multiple of 4 for the program counter, is the reason that you didn't do that because it requires, like multiple reasoning about multiple chips for that, or can that reasoning be isolated to like, on a chip by chip basis?
Yeah. I guess what I'm saying is I can say the most you can say on a chip by chip basis is that if it was a multiple of 4, then it's still a multiple of 4. But you never get the base case of like it started out multiple of 4.
I see.
So unless you're talking about a sequence of chips, there's no. Yeah.
I vaguely remember like some of the chips don't enforce that explicitly, or like don't guarantee that there was like something like a bump chip that you guys used.
Yeah, I think there is like some chip also somewhere that I think does enforce it, like explicitly as well. So in theory, you don't need to like. I think actually for like a full correctness proof, you probably need that. But it is also enforced somewhere. But again, that's not like pulled into these specific chips.
Okay.
Because we specifically just did the ALU, the memory, and the control flow chips.
Okay, thank you.
But I think, Sean, just to jump in about the SP1 chips, I think there are some cases where we don't actually maintain the invariant, and there's like and then that sends an interaction to a bump chip that updates things. If like, I'm not sure if it's PC modulo 4 equals 0, but it could be like that certain range constraints on the PC are satisfied.
Oh, I see.
I think it's something like that. I can't remember exactly, but yeah, that's part of why it's a little hard to reason about. I think you're right, Shankar.
Okay, thanks.
Derek, next.
Yeah, on the like goal for verifying like having proofs over the VM trace over multiple operations, what sort of inductive proof structure would you imagine using for that? Are there any concrete plans?
No, I think the biggest thing is it's hard to, I think, both that and the other things that aren't the DSL change are all, I think, hard to be too specific about without knowing that. Although the basic structure, I think, is fairly clear. Instead of for example, having these instead of just saying that anything that's read from memory necessarily has these U16 limbs for each part of the word, you need to also prove that anything that ever gets written from memory has these 16 limbs, and then show that it's invariant then over everything that's in that table. And so in some sense, maybe you don't even necessarily care that much about the full inductive argument. What you actually really care about, which you can sort of write on a chip-by-chip basis.
Yeah, but then you also have to do all of the memory consistency checks and lookups and all of this to go over full trace.
Yes. There's like many more things.
Doable, but like beyond structuring the inductive proof, you have a lot more things you need to model. Similarly for syscalls as well, actually. Right, because if you did a full trace, you would also have the precompiles and the syscalls you would have to be able to verify. Okay, then
Thanks.
Cody after.
Yeah, so thanks for your talk. One thing I like about this formal verification effort is that it seems to make precise some set of assumptions, but it's still pretty hard to navigate as somebody who's not deep in it, like all of you. So I'm not clear, for instance, whether these assumptions are like specifically described somewhere or if they're just like sprinkled about in various implicit ways in the code, like in the lean code. And I'm also not clear on like which ones are sort of just short-term expediency or kind of like incremental development steps and which ones are like fundamental and forever. So can you kind of give me a sense of how to think about that?
Yeah, I think at least we've tried to, right now they're at least contained within mostly a single file or two, and they're mostly grouped by a sort of category, but they're not, I would agree, maybe documented as well as they could be about whether they're long term or not. I think most of them they sort of have to be, like most of the assumptions are things like immediate values in this RISC-V instruction need to be sign extended to start with, for example. And like there's that sort of assumption that's not even really an assumption about your VM at all. It's just an assumption about the types of programs that you're taking in almost. But then there's also, I would say, any assumption that has to do with table lookups and things like that is potentially something you could evaluate, whether it's needed, because those are the ones that we're sort of taking a shortcut to assume they're there. I think one of the other nice things about using C-Lean, at least as well as I understand it, is that you can actually talk about an explicit like prereq block sort of thing. Like you explicitly specify the prereqs for the circuit as part of the circuit, which I do think is also useful. I think the approach we took was to sort of get all of the assumptions to be really much in the foundations and isolated into a single part of the foundations, which is maybe good for understanding them as a whole, but for each individual chip, it's really hard to see maybe what assumptions go to like that particular chip. I would agree with that. So there is maybe a trade-off there. It might be better in theory to associate assumptions much more closely to chips, but
yeah, I guess I would also add there's a slight difference between you have assumptions from also trusted code bases like the extraction and some what Devon has mentioned, and then you have assumptions that might be done in Lean and essentially introduces additional axioms. But I don't think you have any new axioms in the Lean formalization.
There are two axioms currently that I guess maybe could be removed now. I need to check on the sale extraction, but there's one part where they use a while loop, which is not actually unfoldable in Lean. So we just have an axiom that the while loop like evaluates itself unrolled essentially. But this is in some check for whether memory is like in a valid range for your privilege level also, which is not something where at least currently reasoning about much at all anyway. But so there are those two axioms until yeah, that gets changed in scale.
Eugene?
Yeah, so Cody's question got me thinking a little bit because like one of the assumptions, for example, is that the byte lookups are correct. And that seems like, I think it's sort of assuming that the lookup argument works correct. I'm not sure how we would formalize it. Basically, do you have any thoughts about how that would be formalized? Like it seems like in steps, like first the lookup argument is correct, and second, the actual byte table is correct, or I don't know. Like it's kind of hard to
Yeah,
check that
I
the
mean,
byte table is correct.
you'd first of all, I guess, need to deal with the fact that, yeah, it is just like a hard-coded large table. But then, yeah, you do certainly need like to reason about the lookup argument first, and then I think you would get this assumption as a corollary of some fact about the table and the global lookup argument. I agree that this is maybe it requires a lot of evaluation. I'm not sure how doable or what the scope of this would actually look like.
So for the hard-coded table, could you not verify maybe the codes that generates the values that populate that table? Because for a lot of these, I don't know, if you're doing like a lookup for an XOR, that seems like it'd be fairly straightforward to try to verify.
Yeah, essentially, you could make the table yourself and make the V key, make the like commitment to that table yourself, and check that it matches like the proof.
Yeah, I think no matter what, you're gonna need like some like bridging assumption or thing somewhere. But I mean, that's sort of to be expected, I think.
Yeah. So for context, James, do you want to unmute James? Otherwise, I'll just read out your comment.
Sure. Can you hear me? Otherwise,
Yep.
Okay. Yeah. So we're working on zk-lean, which is another DSL for representing circuits. And basically, there's a few different styles of lookups, but you can basically express your lookup table in the circuit, and then you can just like prove properties about it. So that might be an approach that you could take.
Sure.
Yeah, but then there's also then trying to verify the actual cryptography of the lookup argument, which is like separate thing to verifying the circuit. But it could be done in Enclave, I think. It wouldn't be an issue.
Yeah, I mean, I think having all of these, like a big part of the design was to not try and use Axiom anywhere, right? These are all just predicates on things, which means where we can, if you eventually find a way to get the proof from somewhere else, you can plug it in fairly easily. If you don't, then you don't. But yeah, I think evaluating like what the optimal DSL to represent these things is, I think is important. Like I would like to see more, like I'm not even totally clear what all the scope of the existing work is. It would probably be
on clean on zk-lean.
Yeah.
Yeah, I mean, it's obviously they're both less than a year old, so they're all still evolving a bit. So even zk-lean has been having a bit of a refactor with changing the underlying bonnets. And then clean is probably a bit more stable and a bit more kind of, I suppose, like an all-rounded DSL. But I kind of think in the end, you might want to use like different DSLs for different things. So like for the lookups, like zk-lean is very good for lookups. And so you could just target zk-lean for the lookup specifically and then target clean for the rest. Because zk-lean is probably like not as much of an all-round DSL as clean is. And then clean will also have more specs and templates expressed in clean with kind of product examples verified against this, right? If you're doing catch-ack or anything with an XOR rotation and not all of these basic operations have templates and proofs against them and helpful lemmas. So I can't imagine people will just write like, DSLs for different types of arguments or an extendable DSL to which you can easily add support for one type of argument and maybe have like a specific representation for that makes proofs easier. Like the main appeal of the DSLs in the long run, I think, will mostly be partly the DSL itself and how it represents circuits if it makes composition easier, for example, but also just having a library of helpful lemmas. Because in this case, you were the first ones to verify your constraints against the cell specs, and you wrote a lot of intermediary lemmas. And now, for example, we have the simplified RV64 spec, which is shown equivalent to the cell spec, which basically overlaps quite a bit with some of the lemmas you wrote. And hopefully, like, the more of these lemmas we accumulate for the simplified spec, then the more automation and easy proofs you start to get. And I think that the same will be true if you want to verify like a lookup. Like a lot of it will be, can you extract to a representation that already has lemmas for like compositions of lookups or something like this? Because then if you're able to do that, you save yourself a ton of time, and you start to be able to do, inductive proofs and things like this using lemmas that have been sitting around, before you even started your work. And same with clean, right? Like clean is quite good at having easy proofs for compositions of subcircuits where you can use simp a lot because there's a bunch of lemmas around like composing subcircuits. And like that seems like, if you're trying to do any kind of inductive proofs, like it'll be much nicer. If you have a bunch of lemmas around like, I don't know, the add instructions, and then you have a program to just like a bunch of adds together and then maybe some subtractions, multiplications, and you have like helpful lemmas for all of these, you can just, use simp arguments and lean and have an easier time. But I think this is, it's something that like will just become easier with time as more people do it, rather than something which has to be like a one-time effort, if that makes sense.
Yeah, I mean, I do think there's value to it if we can get like the more of these intermediate lemmas are in a shared place, the more like updating lean to 4, 26, 27, whatever is also easier.
Yeah,
not having so many things to maintain in your own space. Yeah, I think there's quite a lot of code in the project that, probably doesn't belong there. Would better belong.
Yeah, so I'll put a link for anyone who's interested in the kind of simplified, polished, or like handwritten bitblast or RISC-V spec, which is now equivalent to the cell spec. And then like the intent of that repository is to start accumulating helpful lemmas, basically. And being able to bitblast everything.
Yeah. So they can probably take PRs then also.
Yeah. We split it off. We had a chat with Tobias about explicitly splitting off that into a separate repository so that people could do PRs.
Oh, great.
So it should be able to upstream everything. And then the more lemmas, the better.
Yeah, I think honestly, I kind of hopefully not too bad. I mean, trying to splice this, I guess, on the sail end, and then the DSL sort of on the extractor end, and hopefully see how much math can be preserved, I guess, has been my approach so far.
Yeah, I think the other thing that will be helpful is also once the extractions that you have, from Rust or LLZK or whatever DSL you have, are able to target the same monad structure that's used by the cell spec, things might also become easier, because that's also what's going to allow you to access helpful lemmas about this. Because I think right now, otherwise you had to split off all of like the pure parts from the sale state monad for everything, which is a bit cumbersome and like not very ergonomic.
Yeah, the sales state monad still behaves strange. So there were some very strange issues with.
Yeah, so it's changing. We plan on doing this, but it's been a bit slow. But it's changing to a free monad very shortly. If it might have already happened. My next meeting is with the cell guys, so I can update you in an hour. But it's being changed to the free monad, which should hopefully make proofs a bit nicer.
Yeah. Yeah, definitely. Maintainability is not. It's not awful, but it could definitely an area for improvement.
Yes, I had. So I see, Cody, you still have your hand raised. So I don't know if that's because you have another question.
I think you're muted still.
You're muted, yeah.
I do have another. So how do I think about the security of these extractors? I mean, you showed us some extracted code and it was like this god awful complicated thing. And do you have, are there unit tests for these extractors? Does that even make sense? Or would those, what would those unit tests do? I mean, how much code is this extraction for both, I guess, the SP1 and there's like some corresponding thing for the sale? Because that sale is not written in Lean, right? It's like its own language, so you need some step there as well.
Yeah, there's two like extractors, I guess, existing here. There's the sale extractor, which is then like outputting the spec for RISC-V into Lean, and that's like an external tool. I think there's like, I mean, sale itself has tons of people on it, and I don't know how many people. And then for like our side on the SP1 side, I suppose like it's certainly something you shouldn't like take for granted that it's correct, but also I don't know. There's not actually that many as many things as you'd think, because it really just only ever outputs a list of either this thing is asserted to be 0 or like this thing was sent or received via a table, or like you did some math operation. It's just that there's like thousands of these in a line, but each individual one has like is fine, and you can. I mean, there's like the single test. I guess you might wonder.
Sorry, there's like some kind of feedback thing happening with your mic where I kind of miss like maybe 1 in 3 words, but it sounds like you're saying there aren't a lot of, like maybe the output's large, but there's a small number of functions. Can you kind of quantify, like, are we talking about 10 functions, 100 functions?
I should know more, I guess, how big the actual full code is. The actual like Lean backend, to be clear, there's like this symbolic execution that builds in Rust like a syntax tree looking thing. And then that gets output into a Lean string as like a separate backend. So the mapping that says that Rust struct saying this value is 0 maps to the string x equals 0 in Lean. I think I'd trust that like fairly well, because if it's broken, then you should just get like syntax errors and things. The actual symbolic execution, I would say you probably want to look at more closely, but also it's fully within Hypercube, right? It's not public, so. But I really don't think there's very much code there, at least as far as I'm aware. But also the other intern, Gavin, I'd say, looked at it much more closely than me.
So I could share more about the sales side, and then also what we do in the jolt extraction, if that's helpful. So in sale, basically, yeah, they have the DSL, and that's where the RISC-V model's implemented. And then we're extracting it to Lean. So we want to make sure that that Lean is correct and is actually implementing the RISC-V semantics. So basically, since we have the RISC-V semantics in Lean, we can execute it. And there's like a suite of spike tests that we're currently actually still working on this, but we're getting them all to pass. So that'll ensure that they're correct. And then we can also compare outputs to like the C backend. So you can compile the RISC-V to C, and then you can like basically do some property-based testing between the C and the Lean backend to make sure that they're correct. For our jolt extraction, so Devon, I don't know, this might be useful for you guys. So I think we do something similar where we basically like build up an AST of all the constraints. And what we actually do is we have some Rust tests on that like evaluate the AST against the Rust polynomials. And then like that basically gives us some property-based tests that the AST matches the actual polynomials. And then we also do something where we like we generate Lean tests from this. And and then we can execute the extracted AST on the lean side and make sure that that matches the expected outputs. I don't know if that made sense.
What sort of format is it in, like when it initially sort of first arrives in lean? That makes sense.
So our extraction on the lean side looks like it's ZK lean basically.
Okay, sure.
Yep. So and then since we have ZK lean, it's just like circuit semantics, so we can evaluate the circuit, and then like we can check that the evaluations of the circuit match basically what the Rust code evaluated to as well.
No.
Yeah, I don't know. Hopefully that's helpful.
This is probably useful. Yeah.
Yeah, if you want to talk more details, I'm happy to meet and share like what we've done and yeah, what it looks like.
Yeah, you can see the extractor for Jolt is already like open sourced in the Jolt front end, and then there's a ZK lean repository as well that has the lean code. I can link them to you on Telegram after this if you want. So you can run the extractor and generate constraints from the existing Jolt front end, and see what the output looks like and see what the process is. I was going to add one thing as well on the cell side of things, which is that the extraction from cell to lean is fairly general purpose. It's not just RISC-V. So there's also some feedback that comes from the fact that, for example, the people in Cambridge or elsewhere are also looking at, I think, TinyArm and other ICEs in leans through that, which gives us obviously kind of more eyes looking at things on a wider set of cell code. But there were some like minor issues, which were not actually issues in practice, but there was some extracted lean code that might have passed. Anyway, it might have passed something as like a NAT instead of some other integer type that it should be because of ordering in the way a match statement was done. But that was fixed. So there are like very minor things, and then usually it's code that looks weird, but actually like the edge case essentially doesn't come up, and so it doesn't get caught by tests. But it gets fixed very easily. So I don't think we've come up with any like actual bugs that manifested. As far as I'm aware, maybe if you know of any, James, then you can tell us. But
there was,
no,
I think one of those NAT bugs technically like wrong, but it was like wrong enough that it makes the proof impossible, not too easy.
Yeah, so that's like it gets caught that way. I can link the PR that was done to fix the previous one.
Yeah, and I think maybe there's one other issue I can think of that wasn't actually present in the RISC-V model, but the ARM model used some of the features that the RISC-V didn't. So then that was caught and then fixed also.
Yes, I've got the issue here that was fixed. So that's one example of like one issue we encountered. And then this one was also quite weird. I think that issue, it wasn't there initially, and then it occurred because of another change that was done in the extraction from sale. But then it obviously, the edge case never hit, so it didn't really cause actual issues, and then it was spotted, I think, manually, and then fixed obviously as soon as we brought it up and pinged the cell guys about it. So yeah, it's not like, obviously you don't have a formal proof of, I don't know, the cell semantics against the extracted cell spec in lean. Maybe that could be done as like a longer term project in the future, but it is obviously tested and looked at, probably more so than obviously the extractions from, the constraints in Rust to lean. But yeah, I think that brings us at the hour, so I'll stop the recording once I figure out where. There we go.